Hello everyone. In this video, we're going to explain everything you need to know about superpixels and how to achieve them using SLIC algorithm. First of all, what is superpixels and why are they useful? Superpixels are nothing but image pixels that are grouped based on distance and color proximity into macro blocks. The algorithm can be used either artistically or as a pre-processing step in computer vision algorithms. As you can see in the second image, the superpixels clearly separate the butterfly, flower, and background. With subsequent processing steps, another algorithm could potentially isolate and label these subjects. We can also see that the third image is an artistic representation using superpixels. What exactly is a SLIC algorithm? Technically, it is a variation of the k-means algorithm. For each superpixel, we calculate the mean L, A, B color values and mean x and y coordinates of all the pixels it owns. For each pixel, we calculated the superpixel that is closest to that pixel using a 5-dimensional Euclidean distance, taking into account the pixel color and position on the grid. And we mark that pixel as owned by the superpixel. Only superpixels within the permitted window size are considered. As these steps run in a loop, it likely has a significant effect on total system performance. This was the main motivation for optimizing the core algorithm for this project. Now let's take a look at this algorithm in detail.
We'll talk about the algorithm on the left, which is computing the mean color values and mean coordinate values for each superpixel. To do this, we add up all of the values, we count how many pixels there are, and we divide them one by the other. And the step of adding and counting is the summing kernel. We have our array of pixel color values. We have an ownership array that for each pixel indicates which superpixel owns it. And so, for example, all of the shaded pixels are owned by the superpixel at I equals 16 and j equals 11. And then for each ij superpixel, we have a bunch of data that we store, like mean colors and mean coordinates. And the naive way of doing this is just to have a bunch of thread blocks and threads with one thread per pixel, where each thread globally writes that, oh, I found a green pixel at this superpixel value, or I found a red pixel at this superpixel value. Obviously, this is very inefficient because multiple threads can write to the same place at the same time, and so you need to use atomic adds, and so this ends up being very slow, over 20 milliseconds. But what we can do is we can exploit the fact that each pixel can only be owned by one of 9 neighboring superpixels. This is a restriction that also existed in the original Superpixels paper. And with this restriction, we can do the summation in shared memory. So, for example, if you look at this thread block here, we can count how many pixels there are that belong to the center superpixel, how many pixels there are that belong to the right neighbor, how many belong to the bottom neighbor. And then after doing all of these sums for each color channel and for each coordinate channel, we can write the results back to global memory, to the superpixel data structure. And that's much more efficient. You still need atomic adds, but then you do one atomic add per block instead of per pixel. The way this works is we have the sums data structure in shared memory, which is 6 by 3 by 3 by y by x. So we have 6 channels, 3 color channels, 2 coordinate channels, and 1 counting channel. We have the 3 by 3 neighbor grid, so a total of 54 sums. And in each sum, we're summing over the entire thread block. And so we initialize it first. So, for example, sums of 2, which is the B channel, of 0, 1, which is the top neighbor, that gets the B value of the pixel if the pixel is owned by the top neighbor. Otherwise, it gets a value of 0. So after we initialize like this, we sum each one of the 54 different sums using the algorithm in the lecture notes. When we do this, we pick the block size of 32 by 4, which was dictated by the shared memory size limit. We actually didn't get any speed up over the naive approach. But then we thought about using the unneeded threads that are thrown away by the lecture notes algorithm to parallelize over the 54 different sums that we need to do, and that actually got the time down quite a bit to about 7.4. And then we used a short instead of an int for the shared memory array, and that allowed us to use a larger block. We had to use coordinate offsets instead of full coordinates. That got us down to about 5.1. We then parallelized the 54 different atomic adds that we had to do at the end. That got us down to about 4.8. We then eliminated most of the bank conflicts that we saw, and that has got us to about 3.8. And finally, the next idea was to do multiple pixels per thread. That required us to go back to an int instead of a short, because otherwise the sums for the multiple pixels wouldn't fit in a short. Now, when we did this, clearly this had a significant benefit. So going up to doing 32 pixels at a time, this got the runtime down to about 0.8 milliseconds, which is great. And this is the most we could do because we can't exceed the nominal superpixel size of 128. Going further, if we reduce the block size, we can read more at a time, and that got us down to about 0.65 milliseconds. We then optimized the ownership data structure. We used just 1 byte for the I and j coordinates instead of ints. That got us down to about 0.528. And then we did more bank conflict reduction. That didn't get us a lot. We tried getting rid of the atomic adds by basically processing an entire nominal superpixel at a time. That didn't get us anything. And so we thought we were basically nearing the end of what the hardware can do. We did some micro optimizations like loop unrolling that got us to about 0.512. That's actually our final result, 0.512. That's with a 128 by 1 block, reading 128 pixels at a time. We're only at about a fifth of the peak arithmetic performance, only at about a half of the peak memory bandwidth. So our limiting factor here was actually the shared memory size. In fact, if we go to a larger block size and read less pixels at a time, we can get the time down. But the problem is then we need to use shorts, and the sums no longer fit in the shorts, so we get the wrong results. The other interesting takeaway here is about coalesced access to structs, but that's in the report. We don't have enough time to go into this now.
Thank you, Eugene. So now let's talk about the ownership kernel and how it was optimized. The ownership kernel is where pixels are assigned to superpixels. This assignment is done based on a proximity criteria, and in this case, this criteria is the 5-dimensional Euclidean distance. The 5 dimensions are the 3 color channels per pixel, and also their XY position in the pixel grid. We also started the implementation of this kernel with a very naive approach, where each pixel was treated independently. Fortunately though, most of what we have learned from the first kernel was transferable to this one. The first and most important transferable learning is realizing that for each pixel that is aligned with a nominal superpixel, there are actually only 9 superpixels that can own it. So instead of fetching those superpixel data from global memory all the time, it is much more efficient to fetch it once and copy it over to shared memory. Now, this optimization alone was responsible for reducing our runtime by 43%. Rearranging worker threads also led to better performance. We started this kernel using blocks of 32 by 32 threads, but we soon realized that if we could create blocks that covered a whole nominal superpixel at once, the performance would be much better. So here in the right, you can see one of our attempts. In this attempt, we used 8 thread groups, each one covering 128 pixels horizontally and 8 pixels vertically, thus covering a whole superpixel. Now this change alone led to a great performance improvement, but we kept experimenting with it, and in the end, we settled with this arrangement, which was the one with the better performance. Of course, those were not all the improvements that we made to this kernel. As you can see in this chart, we actually went through 11 iterations of improvements. And from those remaining iterations, the transition from the 10th to the 11th is particularly interesting. When we got to the 10th iteration, we measured the kernel's performance with NVProf, and then we realized that our kernel was driving the GPU very close to the maximum number of integer operations that it could do. At this point then, we converted some operations to floating point just to spread the load across different units of the GPU. And then, as you can see, this further improved our performance. But enough talking about the kernels. Let's see some results. So here, you all can see the image of a goldfish. And this is what it looks like after our kernel identifies all the superpixels. And here we have an artistic rendition of the image after each pixel is replaced by its own superpixel's average value. Now let's have a look at what happens on images with more dramatic lighting transitions. Here we can see the superpixels edges correctly identified, and then the pixels replaced by superpixels. And these are results on images with more complex geometry.
The CPU implementation mentioned here is a reference SLIC algorithm which took around 4.5 seconds, whereas the GPU version processed the same in just 71.8 milliseconds, which is 63 times faster. However, the fastest GPU SLIC implementation known to date achieves the 83 times speedup when compared to the CPU version. It is to be noted that only the core kernels were optimized, and that host-to-device and device-to-host transfers were not optimized. Therefore, if this project had optimized all kernels and memory transfers, the overall performance gain would be more than 117 times. Therefore, it is fair to say that the optimizations achieved here are comparable to the state of the art. Even our current runtime allows us to process the video at 14 frames per second in real time. Thank you for listening to our presentation.